This is an interesting scene because 52,000 times the speed of light. Is this the actual speed of light? Where'd this number come from?
Do you know the speed of propagation of subspace radio signals in long-range communications?
I believe it is roughly 52,000 times the speed of light.
Wow, that's super slow.
So my understanding is that nothing can go faster than the speed of light as we understand the universe right now.
Mm-hmm.
Which would mean if there was a speed faster than the speed of light, would that be the new speed limit of the universe?
Oh,
Or
so
something
this
else
is
going on?
this is the question was about the speed of communications in subspace. When in
Okay.
Star Trek, they do these subspace
Yeah.
communications that go faster than the speed of light. Otherwise,
Mhm.
it would be the same speed as our ships. And so 52,000. Why is it 52,000? I don't know.
And
Is
okay, let me.
52,000 a special number?
Yeah. Okay. So first off, how can we not break the speed of light, general relativity, special relativity understanding we have today? And I think it's this. What it's called subspace. So when you want to communicate between 2 points in space, instead of sending a direct beam via light, which would take way too long, you
Mhm.
pop into subspace, travel at the speed of light, and you traverse much shorter distance. And
Okay.
you pop out again, and you send your communication.
Okay.
So this is the like slip space, subspace,
Hmm. I see.
way to get around relativity. I think that's what
And
they're doing, right?
The difference, yeah, I think so. That's exactly right. So the difference in speed for light in the real space versus subspace is a factor of 52,000.
Right.
I guess. I mean,
Yeah.
sure.
Okay.
Um,
And then why 52,000? Well, they're
No
pulling
idea.
in physics of subspace, which we don't have an understanding of in the modern world.
is
'Cause it likely doesn't
52
exist, but is it a special number?
is 52,000 a special number? Okay.
Okay. Well, AI
Um,
says it's not special.
Yeah. AI says it's not special. Yeah. Let's look at it.
Not
So it's not prime. Okay, that's
Okay.
true. Composite which they're saying not prime twice. An even
Yep.
number. Okay.
not a perfect square. So
Let's
it's
maybe
nothing.
ask, is 52 a special number?
Okay.
Yes, 52 is a special number in several contexts, including being an untouchable number. What? A non-cototient? And
Okay.
the number of cards in a standard deck. Oh, okay. I
Oh,
recognize that
okay.
one.
Sure. What's an untouchable number?
An untouchable number, meaning it's never the sum of the proper divisors of any integer. Wait. That's too. Okay. It's never the sum of the proper divisors of any integer.
So I think like say take 6.
hate
Let me see if I can figure this out. I take 6. The proper divisors are
2 and 3.
2, 3, and 6. All right.
And 1?
And we
Is
think we avoid 1 because the word proper might mean not 1.
that- Okay, I guess.
Okay. And then I can add them up. Like 2 plus 3 is 5. Or no,
Okay.
2 plus 3 plus 6 is 11.
Okay, yeah.
So 11 is not untouchable because 2 plus 3 plus 6 is 11.
Okay.
Something like that. So 52, take all the numbers less than 50, or all numbers, all integers, take their divisors, add them up. Those sums will never add to 52.
Okay. Cool. Okay, so as a physicist, like okay.
Okay.
But maybe these means something important in the math world.
Yeah.
I don't mean it in a bad way. I mean like they have their things that are interesting for them.
Well, I mean, it's like when people were doing pure math back in the 1800s, a lot of
Mhm.
people are like, this is never applicable. And then 100 years later, in computing, it becomes super applicable. So
Yeah.
even if it seems silly now, it may not be silly in the future. So
That's a very good point. I mean that's the same story as quantum mechanics, where physicists encountered quantum mechanics and then they looked over at linear algebra like, oh my gosh, this is the same thing. This is exactly what we needed. It's already been solved
Exactly.
by someone 100 years ago.
the mathematicians, keep doing your thing, please.
Please. Yep, super important. Non-cototient, meaning it's not equal to x minus phi of x for any integer x, where phi of x is Euler's totient function.
Okay.
What? Okay. I read it. Let's look
Okay.
at it.
What is totient function?
Totient.
Totient.
Okay, well that's non-cototient and
Well, there it is. Euler's totient function.
Euler's totient function.
Okay.
In number theory, Euler's totient function counts on the positive integers up to an integer n that are relatively prime to n. What? Please decode
Okay.
this.
So if there's a number n, and
For
if
example.
two numbers, let's just do the example.
Okay, let's do the example. Okay, for example, the totatives of n equals 9 are the 6 numbers 1, 2, 4, 5, 7, and 8. Okay. They're all relatively prime to 9, but the other 3 numbers in this range, 3, 6, 9, are not, since GCD.
The greatest common denominator?
Thank you. Greatest common denominator 9, 3, 9, 6, 9, 3 are all 9. Therefore, this Euler's function of 9 is equal to 6. As another example, 1 is 1. The only integers in this range of 1 to... Okay.
I see.
Cool.
I
Some
think,
math undergraduate is laughing at me right now.
Yeah.
What is this?
I think two numbers are relatively prime if they don't share any common denominators.
Okay, so
then
5 and 7 don't share a common denominator, so they're relatively prime.
They're relatively prime, and they're also both prime.
Okay, bad example.
Yeah.
So 4 and 9, they're both not prime, but
Right.
their common denominators are none because they would have been
None.
2 and 3.
Right. Exactly. So they're
Okay.
relatively prime,
Okay.
but neither are prime.
Okay,
And then this takes the number n and counts how many relatively prime numbers are below that. Or relatively prime to n. How many numbers are relatively prime to n? And you would expect that number to get higher and higher as the number gets higher and higher. And it looks like it's weirdly linear. I'm looking at that graph over there. That's kind of weird.
So this is the first 1,000 values of this function.
Mm-hmm.
Top line represents the function where p is a prime number, which is p minus 1, and it's weirdly linear. Yeah, that is weird.
Yeah. And like there's other patterns too. There's like sublines below.
Yeah, why is there structure to this?
See, this is why mathematicians do their thing, because they're like, this is so, I would expect this to be a scatter thing, but then it's like, why is there a weird structure? And then they figure it out.
I see it. I mean, in some sense, this is, yeah, I've heard this many times. Math is the purest form of physics because it doesn't care about any of the particular dynamics. This is straight up how numbers work. And the numbers are showing us there's weird ways that numbers work. How else to say that?
Yeah.
It's some statement of this is how our world is.
Mm-hmm. So super cool, but maybe the number 52,000 isn't special in a number way. I mean, it's got some cool properties, but
that being said,
sure.
There is something cool about this. In fact, like kind of mind-boggling to me, is that we just explained this quotient, non-cototient idea, and all we had to deal with was prime numbers. And while it did feel, for me at least, very abstract and very weird, prime numbers is something that we learned in school in something like 4th-ish grade, maybe.
Yep.
4th-ish. So that's a 10-year-old, maybe 11-year-old.
Yep.
And so you can get to some high-level math with just the understanding, like the minimum parts you need was prime numbers, which people get access to when they're 11, 12 years old.
Yeah, it's even cooler than that. If you know Goldbach's conjecture.
I don't. Let's look it up.
As soon as you learn prime numbers, you can immediately say an unknown problem in mathematics that nobody has solved ever. Like, wow.
Oh. Okay, first let's read it. Goldbach's conjecture is one of the oldest and best known unsolved numbers and problems in numbers theory and all of mathematics. It states that every even natural number greater than 2 is the sum of 2 prime numbers. Is there an example of this? Easy example. Maybe you can give us an example.
Let's see. The number 10 is 5 plus 5.
Yep.
So 10 is the sum of 2 prime numbers, which would be 5 and 5. Also 7 and 3. And so this says that all numbers 0 to infinity are the sum of 2 prime numbers. And I think this has been tested through computers all the way up to 10 to the 50 or whatever, some huge number.
Huge.
But it hasn't been proven for all numbers yet. So it's such a simple statement that you could teach somebody like a 10, 11, 12-year-old who just learned prime numbers. You could teach him a problem that has no known solution. Like, wow.
Just because let me understand what you're saying. So that it's been demonstrated that this is true, that you can take any even number and it'll be the sum of two prime numbers. You can demonstrate that it's true, and it's been demonstrated by computers up to 10 to the 50, some enormous number. But the fact that it works is different than the fact that it should work. So it's not been proven. Like it should be true for this reason. It's just so far it seems to be working.
That's right. We can't do an exhaustive search because we would have to do it for all integers.
To infinity. Never going to happen.
Infinity. You can't do an exhaustive search.
You can't.
So you'd have to come up with some reasoning of why it's true for all integers, and we don't have one. Like crazy. What a simple.
That's incredible. That's incredible that all you need to know is prime numbers and addition, and that's like 4th grade, maybe 5th grade knowledge, and you could immediately at that age, it's someone's youth, so that's like 10, 11 years old, they could be exposed and start tackling this unknown, like unsolved mathematics problem. Like the barrier to entry is pretty low.
Pretty low, yeah. Incredible. I wonder, we shouldn't look it up now, but I wonder why that's such a hard problem. Like, why do people know why it's hard? You know,
Also an interesting question.
Seems like it's easy, but hard.
It's like so easy in concept, but to prove it is challenging.
Right.
I'm not a mathematician.
Yeah.